All right, deep learning exam tomorrow. Feeling the heat? Don't worry, you're in the right place. We're going to break down a really important paper by Cynthia Rudin, and trust me, it challenges a lot of what we think we know about AI. Getting this won't just help you on the test, it's about understanding where the entire field is heading. Okay, let's just jump right in with a big question, the one that gets to the heart of everything. Think about it. A major decision, maybe about your health or even someone's freedom, is on the line, and it's being made by an algorithm. How would you feel if nobody, not even the experts who built it, could actually tell you why it made that choice? That's the core problem we're going to unpack today. So here's our roadmap. First, we'll nail down exactly what the black box problem is. Then, we'll talk about why trying to explain them is actually a trap. Next, we're going to bust a huge myth about accuracy. After that, we'll look at the alternative, interpretable models. And finally, we'll ask why we aren't using them more. 5 simple steps, and you'll have this down cold. All right, part 1. Let's start with the absolute basics. You hear the term black box all the time in AI, but what are we really talking about? Let's get a super clear definition so we're all on the same page.
Okay, this is a key definition, so lock this one in. A black box model is one of two things. Either it's just mind-bogglingly complex, like a deep neural network with millions of connections, so tangled up that no human can really follow the logic. Or it's a company's secret recipe. It's proprietary, locked up so no one can see how it works. Either way, the result is the same. We can't see inside. We just get an answer with no reason why.
And make no mistake, this is not just some academic debate. This is happening right now, in the real world. And when these models mess up, the results can be devastating. We're talking about real people being denied parole based on a faulty prediction, or pollution models telling us the air is safe when it isn't. The stakes are just incredibly high. So, you might be thinking, okay, if the box is black, why not just build something else to explain it? Sounds logical, right? Well, that's the idea behind something called explainable AI. But, as the paper argues, this path leads straight into a trap. So, the go-to solution right now is to create a second, simpler model whose only job is to try and explain the first complicated one. This is called a post hoc explanation, meaning it happens after the fact. It's kind of like trying to guess what's in a wrapped gift by just looking at the shape of the box. You're making an educated guess, but you don't really know. And here is the killer logical flaw. You're going to want to remember this for the exam. The explanation model has to be an approximation. It can't be a perfect copy of the original black box. Think about it. If the explanation was perfectly faithful, it would be just as complicated as the original, and you could just use the explanation model instead. So you're stuck with an explanation that you know is wrong at least some of the time. The problem is, you have no idea when.
This slide is the perfect example of how wild this can get. So the model correctly identifies the picture as a Siberian husky. The explanation, this heat map thing, shows us the pixels it was supposedly focusing on. You can see it's lighting up around the dog. But now look at the explanation for why this same model might think this is a transverse flute. The heat map is almost identical. This tells you where the model is looking, but it tells you absolutely nothing about why it's making its decision. The explanation is totally useless.
Okay, so if the explanations can be so bad, why do people keep defending these incredibly complex models? Well, that brings us to what might be the single biggest myth in all of machine learning. For years, there has been this belief, almost like a law of physics in AI, that there's a trade-off. To get the absolute best, most accurate predictions, you have to use a complex black box. And if you want a simple model that you can understand, well, you're just going to have to accept lower accuracy.
And this chart right here is Exhibit A. It came out of a big U.S. defense research program, and it's been shown everywhere. It shows this clean, smooth curve. As your model gets more explainable, its performance just has to go down. It looks so official, so convincing, doesn't it? Well, here's the secret. That chart, it's completely made up. It's a cartoon. It's not a plot of real data. It's just an illustration of what people believe to be true. And what this paper argues very powerfully is that for a huge number of real-world problems, especially with structured data like you find in criminal justice or finance, this trade-off is a total myth. You don't have to choose.
So if explaining black boxes is a trap, and the accuracy trade-off isn't real, then what's the alternative? This leads us to the big solution proposed in the paper. Just use interpretable models from the start. The idea here is to completely flip the script. Instead of building something complicated and then trying to explain it, you design the model from the ground up to be understandable.
It's built with constraints so that a human can just look at it and get it. It doesn't need a separate explanation because the model is its own explanation.
And this table just lays it out perfectly. On the left, you've got Compass, a famous black box model used in the US justice system that uses more than 130 different factors. On the right, you have an interpretable model called Corals. It uses just 3 simple if-then rules. And now look at the bottom line. Their accuracy is basically identical. All that extra complexity in the black box buys you absolutely nothing in performance, but it costs you everything in transparency. And check this out. This is the entire Corals model. That's it. 3 rules. A judge, a lawyer, anyone can read this and understand exactly how the recommendation was made. There's no mystery. It's all right there.
Here's another flavor of an interpretable model. It's just a simple scoring system. It looks like a checklist a doctor would use. You just go down the list, you add or subtract points for a couple of key things, and the final score gives you the risk assessment. It's simple, it's easy to double check, and it works.
Now, you might be thinking, okay, this is great for tables of data, but what about something really hard like computer vision? Well, it turns out you can design interpretable deep learning models too. Instead of just spitting out, that's a sparrow, this model actually shows its work. It says, I think this is a sparrow because this part of the image looks a lot like other sparrow heads I've seen, and this part looks like the wing feathers I've learned. You can literally follow its logic. So if these interpretable models can be just as accurate and they're transparent and easy to trust, why aren't they everywhere? Why are we still so obsessed with black boxes? That brings us to our final section. It really comes down to a few key reasons. First, business models. You can sell a secret, proprietary black box as intellectual property for a ton of money. It's a lot harder to do that with a simple set of rules. Second, it can actually be more computationally difficult to find the best simple model than it is to just throw a ton of data at a huge neural network. And third, it's a training issue. Most data scientists today are trained to be experts in deep learning, not necessarily in these other interpretable methods.
And so that leaves us here with a big takeaway question, the one I want you to have in your head for the exam. The focus in AI right now is all about, can we explain the black box? But maybe that's the wrong question. Maybe the real question we should be asking is, why did we build a black box in the first place, especially when the stakes are so high? If you understand that shift in perspective, you've understood the whole point. All right,